Okay. So hi students. So today we'll start with our new lecture. We have already covered like the multiplexer. So now this is a multiplexer. Can you see here? So now if you look at this multiplexer, everything is visible to you. Yes. So if you look at this multiplexer, so look at the block diagram of the multiplexer. Okay. And please, if you want an easy exam, so please answer my questions very quickly in 5 seconds. Okay. If we look at the block diagram of the multiplexer, how many inputs are there to this multiplexer? It's a 2-to-1 multiplexer. How many inputs are there? Can you tell me? Please, quick. How many inputs are there to the multiplexer?
Two
This is the
inputs.
multiplexer. Huh?
Two inputs.
No. Three inputs.
Oh, and the selector.
Yeah, so we have three inputs D0, D1, and the selector line S. Got it or not got it? So now you can see here there are three input D0, D1, and select. And what is my output? Can you even tell me what is my output? Anyone may help. Please be quick.
Why?
Why? Okay, now if you look at here, so now if you look at here, so how many inputs are there? There are three inputs. If there are three inputs, so how many combinations are there? So there are 2 to the power 3, which is actually 8 combinations. Got it or not got it? So these are 8 combinations. So with this, now there are three inputs. And since there are three inputs, how many combinations are there? Help me. 8 combination. Got it or not got it? Okay, now if you look at here, when S is equal to 0, now there are two possibilities. Either S is equal to 0. So when S is equal to 0, now please look at, this is the red color. Now using the red color. When S is equal to 0, what will be the value of my Y? Can you tell me? What will be the value of Y?
0, 1, 0, 1, 0.
So Y will be the same thing as D0 or D1? Help me.
SD0.
D0. So Y is the same thing as D0. You got it or not got it? So this is now the truth table of. Okay. Now when S is equal to 1, which color? Please help me if you are not like looking at the color coding. Which color? If I do not get an answer in 5
Blue.
seconds, you know the consequences. Yes. S is
Blue.
equal to 1. Blue color. Very good. So when S is equal to 1. So can you see here when S is equal to 1? What is the value of Y? Can you help me? What is the value of Y? Y is equal to
D1.
D1. And what is the value of D1? So the value of D1 is this thing. So now can you see here Y is the same thing as G1. Any question? Got it or not got it? Is clear or not clear?
Clear, Professor.
Okay, very good. So at least I need your answer. Okay. Now when we need to see these things. So now there are two possibilities. Now please remember, now we are with the red color. So when we are red color, when Y is equal to Z, when S is equal to 0, when S is equal to 0, who will pass on the output? Can you tell me? Who will pass on the output? When S is equal to 0, so red color. So Y will be equal to D0 when S is equal to 0. And when Y S is equal to 1, so S is equal to 1, what will be Y? Y will be equal to D1. Any question? Any question? Clear or not clear?
Clear, Professor.
Very good. Thank you. Thank you. Thank you for your prompt answer. It means that you want an easy exam. That's good. That's good. Okay. Now let's check it. Now this is the, now if you look at here, the block, the 2-into-1 multiplexer, and this is the gate level diagram, the gate level diagram of a 2-into-1 multiplexer. Got it or not got it? So now if you look at here, if you look at this gate level diagram of this multiplexer, so there are two possibilities. Got it? When S is equal to 0. Got it or not got it? So when S is equal to 0, so the first possibility, which color? Which color is this? S is equal to 0. This color, when S is equal to 0, S is equal to 0. So this S is equal to 0. So S is equal to now 0. When S is equal to 0, so what will be S bar? S bar will be equal to 1 because this is an inverter here. So S is equal to 0. So this will be S bar will be 1. And then we have A dot 1. And what is A dot 1? And A dot 1 is what? Help me.
A.
A. When S is equal to 0, okay, the first input is 0. So the output of this, it is actually B dot 0. And what is B dot 0? So B dot 0 is equal to 0. So now we have 0 here. And now we look at this OR gate. So this OR gate is, will now compute what? A plus 0. And what is A plus 0? It is actually A. So when S is equal to 0, C, which is my output, is equal to 1. A. Any question? Clear or not clear?
Professor, I don't get why it's A.1 if it's
Which
S is
one?
0. Why is it A.1 if S is 0?
Because there is an inverter here, there is a bubble here. Can you see the bubble here?
Oh, okay. I thought that's a
You
0.
got it or not got it?
Yes.
Because there is a bubble here. So basically, there is an inverter here. I'm saying, okay, there is an inverter here. Very good. Got it? Any
Yes,
question? Okay, now I'm looking like the blue color, and this is the same diagram. This is the same diagram. Okay, now I'm not also drawing it. So this is the inverter here because very good, because at least you're paying attention. Thank you. You're paying attention, and you really like it. When S is equal to 1, what will be the value of C? Help me. A or B? So you'll be equal to B
It's
when S is equal to
0.
1. S is equal to 1. So basically, the first input is 1. The second input is B. What will be the output? B dot 1. And B dot 1 is what? B. Now, when S is equal to 1, so we have a 0 dot A, because S is equal to 1, we have an inverter, so A dot 0. What is A dot 0? Help me.
0.
0. And now if you look at this OR gate, so it is actually B plus 0. And what is B plus 0? So C will be equal to B.
B.
Any question? Any question? Am I recording or not?
Yes,
you're
recording.
Okay. Yeah. So basically, I want, because I want the thing to. Any question? This is clear or not clear? Clear? Should I proceed? If I'm not hearing an answer, this is not a good sign. No answer? Anyone?
Yes, it's clear.
Good. That's good. So can you see here, when S is equal to 0, so basically the same thing. When S is equal to 0, A will come. And when S is equal to 1, A will come. This is how it works. This is the reduced table. Got it or not got it? This is how it works. This is now the selected. And now we can see here. Now please look at here. So now if you look at here, so now we want to find, and now I'm now using different colors. Okay, I'm now using different colors. So can I write this thing? So I want to draw the gate level diagram of this thing. So can I write something like this? So now I'm using Y. So Y is my output. And now using the green, red. So if it is 0 0, if it is 0 0, so can you see here? This is 0 0. The first thing is, so what will pass? D0 will pass. So it means actually it will be what? S1 and S0 and D0. Where should I put bar? Can anyone tell me? Help me. Where should I put bar? Anyone may help. I'm not getting any answer. So this is actually 0 and 0. So S1 and 0 is 0. So if
S1
they are
and
0 0,
S0.
D0 is 1.
Do you
Where
put
should
the
I put
bar
a
on
bar?
S1 and S0?
Yes, very good. S1 and S1 and S0. Now I'm using another color. I'm now using the green and the blue color. So basically it is actually 0 1. If it's 0 1, D1 will pass. What will be the expression? S1, S0 and D1 plus. Where should I put a bar? On S1 or S0? Help me.
S1.
S1.
S1. Very good. Now I'm using a green color. So this is 1 0, which is the binary of things. So this we have S1 and S0, and then D2. Where should I put a bar? Help me. S1 or S0?
S0.
1 0. So S0 and plus. And then I'm now putting another color. So basically that color, I'm now short of some color, so I can use this color. Okay. So S1 and S0, and then D3. This is actually 1 1. Any question? This is clear or not clear?
Clear.
Clear? Okay, now what I'm going to do, so now we want to draw the diagram for this. So can you see here? So we want to draw the diagram. Now I use all the colors. Okay, now we are using all the colors. Okay, so now I'm going to draw the diagram. So now please look at the red diagram. So now red diagram is very simple. No, it's very simple. So now we have the red color. So now we have the red color, which is actually the S1 bar. So we have S1 bar is here. Then we have S0 bar, and the other input is D0. Got it or not got it? So this will come here. Then we have the another term, which is actually what? Now I'm using the blue color, S1 bar. So this will S1 bar will come here, and then S0 will come here, and then I will need D1. So this is also here. Then we are using now the green color. So now the green color is actually S1. So we are getting S1 here. S1 will come from here. The second input is S0 bar. So S0 bar will come from here. And the other input is actually D2. So D2 will come here. Any question? And then we have this color. So we have what? S1. So S1 will come here. And then S0. So S0 will come here. And then we have D3. And what we should put in the end? Can you tell me what should we put in the end? Help me.
Y. And or.
No.
Oh.
An OR gate.
Yeah, an OR
And now
gate.
use the black color because this is an OR gate for the black color, and now we have an Y. Any question? So basically, if you look at here, so now if you look at here, so it means that now we can generally say how many AND gates are there. So, okay, got it or not got it? Any question? Clear? So now if you look at here, for this example, now if you do that, so how many AND gates are required? How many AND gates? Help me. Question 1. How many AND gates? Help me.
4.
4, 3 input.
Yes, 4. But how many AND gates? 4. How many AND gates? 4. 4, 3 inputs AND gate. Also the type of that gate. How many gates and what type? Now question number 2. How many inverters?
2
Help me.
inverters.
2 inverters. Question 3. How many OR gates?
1 OR gate.
1. Type. Type is important.
4 input OR gate.
Got it or not got it? Any question? Is it clear? Any question? Okay, now what I'm going to do, so now I'm going to draw the same figure. No, we draw this figure, sorry. Got it or not got it? So now let's assume this is, when you say here, so now what are you going to do? Okay, so let's assume if the value of, now I'm now using some color, so I'm now using the black colors. Okay, black color is now I'm using the, let's assume the value of S1 is, so okay, now let's assume the value of S1 is 1 and the value of S0 is 0. What should be the value of Y? Can you tell me? Help me. I want an answer, quick answer. What will be the value of Y?
Is it 1?
Wrong.
D2.
Very good, D2. Now let's prove it, and you can do it for anything. So when S1 is 1, so now S1 is 1 now. Okay, so in S1 is 1, so this, the input to this gate will be 0. So in the gate, in any input to the gate 0, this will give me 0. You got it or not got it? So I just ignore it because any input to the AND gate is 0, the output will be 0. Now S0 is 0. Clear? S0 is 0. So S0 is 0. So S0 is 0. So any input to this gate is 0. So we'll ignore odd one, so the output is 0. Any question? Clear or not clear? Okay. When S0 is equal to 0, when S0 is 0, so it means that this will invert the value. So this will give me a 1. S0 bar will be 1. And this one will come here. So this will be 1 here. And now S1 is 1. Since S1 is 1, so this S1 is 1 and S1 is coming here. 1 is 1. And then we have 1.1.d. So it is actually 1.1.d2. This will give me D2. And okay, now look at the last thing. Now S1, please look at S1 is now 1. S1 is now 1. What about S0? S0 is 0. So 1.0.d3. So what will be the output? 0. So if you look at this y, so this is actually 0 plus 0 plus d2 plus 0, which is actually d2, and now y is d2. Any question? Any question? This clear or not clear? Yes
Professor,
or no? I'm not hearing an answer. If I'm not hearing an answer, it is not good for your.
Professor, I had a question.
Please. Yes,
It's
please go
not
ahead. Yes.
exactly related to the logic of the multiplexer, but
Yes,
you know
that's
how,
something that logic of the multiplexer. So it means that now we have 4 gates. So we have G1, G0. I call it G0, G1, G2, and G3. So it means that G0 will be enabled because G0 will be enabled. It will pass G0 and all other will produce 0. You got it or not got it? And G1 will pass D1. G1 will pass T1 if it is 0, 1. Other will be 0. Got it or not got it? Any question?
yes, Professor.
This is clear?
Yes.
Very good, very good. And it's a very good question. This is how the logic of the multiplexer is. Got it? So now what we are going to do? So now can you see here? Okay, now what I'm going to do? So okay. And now this is can you see here? So in the exam, I may also ask some questions. So what is this thingy? So this is 0 0. So this if S1 is 0 0, so D0 will pass. If it is 0 1, D1 will pass. If it is D2, 1 0 will pass. There is some animation. Please go through this. So what is this thing? This thing is the gate level implement. So if you look at here, what is this thingy? This thing is the gate level implementation of a 4 to 1 multiplexer. It is the gate level implementation of the 4 to 1 multiplexer. And what is this thingy? This thingy is the gate level implementation of a 4 to 1 multiplexer. How many AND gates are 4 to 1 multiplexer? How many AND gates are required? There are 4 3 input AND gates and 1 4 input OR gate. So this is also the gate level implementation of a 4 to 1. So this is one way to draw it, and there is another way to draw it. You got it or not got it? So there is the same thing. Any question? Is clear or not clear? Okay. So now if you want to draw, so now let's assume if you want to draw an 8 to 1 multiplexer. So now we have an 8 to 1 multiplexer. Now let's assume we have now an 8 to 1 multiplexer. This is very important. This is 8 to 1 multiplexer. Okay, so now how can we draw the reduced truth table of this 8 to 1 multiplexer? So the reduced truth table will look like this. So we will have S2, S1, and S0. And there will be a lot of combination. Let's assume that I'm now using different colors. So let's assume we are using a red color. Okay, so the red color means this is 4, 0, 1, 2, 3, 4. So 4. If you do, what is the code for 4? Can you tell me? Help me. 100. So the code for 4 is 100. When S2 is 1, S1 is 0, and S0 is 0. What will be the value of Y? Can you tell me what will be the value of Y?
D4.
Anyone may answer? Huh?
D4.
Very good. So Y will be equal to D4 because D4 will go through. Okay, now you can put and let's assume we have this, assume we have the green color. Now I'm using the green color. So let's assume if we have, it is 001. So let's assume, so this is 001. So now I'm using a green color. What will be the value of Y? Anyone may help me.
D1.
Very good, very good. Now let's assume now I'm using another color. So you can fill the table. So you can fill that whole table. I'm not just looking like it's like the reduced table. So let's assume if it is 7, it is 1 1 1. What will be the value of Y? Anyone may help.
D7.
Got it or not got it? Any question? Clear? So what I'm going to do is I'm going to say the same thing, and then I can do it here. So how can we draw the gate level diagram of 4 to 1 multiplexer? 8 to 1 multiplexer. What is the gate level diagram? So this is very simple. So what I'm going to do, so Y is equal to, so now what I'm going to do, because I'm not using any colors coding because it will take a lot of time. So so basically if I want to draw it, it's very simple. So I can write S2, S1, S0, okay, plus S2, S1, S0, plus S2 S1 S0 plus S2 S1 S0, because there are 8 combinations, so we need to fill all the combination, plus S2 S1 S0 plus S2 S1 S0 plus S2 S1 S0 plus S2 S1 S0. Got it? So now how can we do it? So for the first combination, so the first combination is 0 0 0 0 0 0. What should I put? Help me.
Bar and D0.
No, S2 bar, S1 bar, and S0 bar, and then D0. Bar on all the select line. Got it? Got it. So this is actually, so if you look at here, the thing, so now this is actually, okay, now I'm looking at the red one. Now I'm looking at the red one. Since the red one, so it is actually, what is the code for one? The code for one is 001. So it is actually 001. So what should I write? Help me. Help me,
Bar,
please. I want
bar,
your help.
D1.
Yes, S2 bar and then
S1 bar and then D1.
Got it or not got it?
Yes.
Okay. Now I'm now putting another color. Okay, now maybe I will use some color. So now we can see. So this is actually, what is the code for 2? This is 010. So this is 010. So what should I put? Help me. Help me.
S2 bar, S0 bar, and then D2.
And similarly, you can do that. So this is 011. So now, so now I can stick with the black color. So I'm not going to do it now. So this is actually, this is 010. So this is actually 011. So this is 011 and D3, and then 100, then D4, then 101 and D5, and then 110, D6, and 111, D7. Any question? Any question? Clear or not clear?
Clear.
Okay. So how many? So okay, question number 1. How many AND gates? Answer me.
8
How
AND
many
gates.
AND gates?
You input
Hmm?
8 AND
So we
gates.
have 8. What type?
3 input. No, 4 input.
4 input. And you can draw the diagram. I'm not going to draw the diagram, but you can do the diagram. Question number 2. How many OR gates?
1 8 input.
1.
1 8 input. How many inverters?
4.
3 inverter.
Who said 4?
My bad, 3.
3. Good. 3. Because we have 3 select lines. The number of inverters will be equal to the number of select lines. Got it? Any question?
Professor, so
Yes.
for this, it will be 11 input
For what?
for the
Yes.
multiplexer?
Yes, there are totally no inputs. Yes, you're right. Totally right.
Okay.
Any question? Well, very good observation. Very good observation.
I don't get why it's 11.
Which one?
I don't get why the multiplexer will have 11 inputs.
Because, okay, no problem. Yes, very good. Very good. And it's also, if you are asking a question, I'm very happy with the questions. Very happy. Because these are 8 and these are 3. So 8 plus 3 is 11. Any question?
Okay, thank you.
You got it? Or no? Because S2,
Yes, I
S1,
got it.
S0 are the inputs. Got it? Okay, now if you look at the E1 to how many inputs are there? So this is D0, D1, D2, and D3, and S1, S0. There are 6 inputs here. And if you look at a 2 to 1 multiplexer, so now let's say if you look at a 2 to 1 multiplexer, so there are 3 inputs. Remember this? So we already did it. You know, if you look at the block diagram, so these are 2 inputs and there are select lines. You got it or not got it? I hope I answered your question. Yes or no?
Yes, thank you.
Okay, so now what we are going to do, oh, this is now a $1 million question, and this is a very important question. Okay, now what we are going to do, so we okay, now please remember, now we can see here. So now at this point of time, we can say this is the, what is this thingy? This is the gate level implementation of a 2 to 1 multiplexer. Now, if you look at here, this is the gate level implementation of a 4-to-1 multiplexer. And now here, this is not the gate level implementation. This is actually the Boolean expression of 8-to-1 multiplexer. And you can draw the gate level diagram. I'm not doing it because I don't have any time to draw it, but you can. It is your homework. You can draw the gate level diagram of a 8-to-1 multiplexer. Okay, so now these are the different diagrams. But now the million-dollar question is this: how can we? The question is this. This is the question, and this may be the question in exam. So I need your attention here. Please remember, this is a very important question. This, when I say important question, I need your attention. So we want to do that thing. How can we design a 4-to-1 multiplexer using 2-to-1 multiplexer? Okay, we are not going to design using gate level. We are using the hierarchical design approach. In hierarchical design, we are using multiple blocks. Now, if you look at the block diagram of a 2-to-1 multiplexer, so now we have a 2-to-1 multiplexer. So the 2-to-1 multiplexer will look like this. So we have actually 0, and then we have 1, and then we have S line, select line, and let's assume we have output Y, and this is actually D0, and we have D0. Got it? This is the block diagram of a 2-to-1 multiplexer. Any question? So how can we design this 4-to-1 multiplexer using 2-to-1 multiplexer? So to do that, we need to analyze this 4-to-1 multiplexer. If you analyze this 4-to-1 multiplexer, I'm now going to draw the truth table of this 4-to-1 multiplexer. If you draw the 4-to-1 multiplexer, so if I look at the block level, it's just like at the block level. If I look at the block level of a 4-to-1 multiplexer, so this is a 4-to-1 mux. And if you look at the block level, so the inputs are D0, D1, D0, D1, D2, D3, got it? And then S1, because they're through select line. And S0. And what is my output? Can you tell me? Why? Any question? Is clear or not clear? Clear or not clear? Okay, now we want to draw the truth table of this, because to design this thing, we need to draw the truth table. So how can we do that? So now I'm going to draw the truth table in the red color. So can we see here, now we have 4 inputs. So we have S1 and S0. S1. And then we have S0. And then we have Y. I'm using some color, and there is a reason for that color. Okay, how many combinations are there for S1 and S0? Can you tell me how many combinations are there for 0? So it is 0, 0, 0, 1, 1, 0, and 1, 1. What about S0? So at 0 is 0, 0, 0, 1, 1, 0, and 1, 1. Got it or not got it? So I'm just like using different colors. Why I'm using different color, I will explain this later on. What will be the value of Y when they are 0, 0? What will be the value of Y? Can you tell me? What will be the value of Y here? S1, S0 is, please help me. I'm not getting answers, so it means it's not a good sign.
D0.
D0. Then D1, this D2, and D3. This is clear or not clear? If this is clear, I can proceed further. So what I'm going to do now, so I'm going to copy and then I'm going to paste it here. So this is just how it works. So now we want to do this thing. Does someone make any observation using this thing? So I'm now going to write some comments. Okay, so now what I'm going to do, so I'm now making some observation. Okay, so let's assume if you look at the truth table, so if I'm now using the black color, when S1 is equal to 0, what should be my comment? What should be my output? Can you tell me? When S1 is, I'm ignoring S0. I'm just looking at S1. What can I write? What will be my output Y?
It will be either D0 or D1.
Yes, very good. It will be either D0 or D1. Now looking at another input. So now let's assume I'm now making another logical argument. And my argument is that let's assume my S1 is 1. What will be my output? Can you tell me? Can you help me? Yes?
D2 or D3.
D2 or D3. This is clear or not clear? Okay. So now can I say now make and see? So what you can say? So now in my comment, so it means that y will be either d0 or y will be equal to d1 or y will be equal to d2 or y will be equal to d3. So I can make an argument. So I can use a multiplexer here, and the output of this multiplexer will now depend on S1. There are two possibilities of S1. S1 is 0. We're now using the black color. The black color. S1 is 0. And if S1 is 1, I'm now using this orange color 1. And the output of this is Y. So if S1 is 0, what should I write here? When S1 is in the black color, what should I write here? On this line. Help me. Please help me.
D0.
D0 or D1, we don't know. You got it and I got it.
Yeah, got it.
Okay. Now if I'm writing, if I'm in now it 1, what should I write on the orange color? Can you help me? Help me.
D2 or D3.
D2 or D3. Now whether D0 will pass or D1 will pass will now determined by another multiplexer. So we need another multiplexer here. Because I'm now building in logical argument, so we need another multiplexer here. So we need another multiplexer. And now this value of multiplexer now depends on S1, S0. So if S0, so now we can put the select line 0. There are two possible values, 0 or 1. If the value of S0 is 0, who will pass? Help me.
D0.
D0 will pass. And if it's 1, who will pass?
D1.
D1 will pass. Now I'm using another color. So now what I'm going to do, I'm now using another color, and now I'm using this. Did we use blue color? No, we didn't use blue color. So I'm now using a blue color here. So please look at here. So now please look at here. So it means that it will be 0 or D1. So it will 0 or 1. So this is this multiplexer here. Now we are in D2 or D3. So now I'm now in this line. So if I'm looking at the sorry, no, I want to have the blue color, not this color. Blue color. So now it also depends on S0. So there are two possible values of S0, 0 or 1. Help me. So if it is 0, who will pass?
D2.
D2. And if it is 1?
D3.
So in the exam, if I ask you a question, like design a 4-to-1 multiplexer using 2-to-1 multiplexer, so this, and I give you the truth table. So you will draw this diagram. If I give you, okay, design this 4-to-1 multiplexer using the gate level approach, so you will draw this diagram. You got it or not got it? Any question? Any question? Clear or no?
Clear.
Okay, now following the same argument, what is now now what is our objective? In the previous example, we designed a 4-to-1 multiplexer using 2-to-1 multiplexer. Now we are solving another problem. We want to design, okay, an 8-to-1 multiplexer using 4-to-1 multiplexer and 2-to-1 multiplexer. Got it or not got it? Any question? Clear? Okay. Now what is our logical argument? So now we can see here. So let's assume we have 3 inputs, which is actually S2, S1, and S0. So these are 8 possible combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Got it or got it? What should be my y here? Can you tell me what is my y here? 0, 0, 0. I'm not getting any answer. It means you slept.
D0.
D0, D1, D2, D3, D4, D5, D6, and D7. Got it or not got it? So this is the block diagram. Now what I'm going to do is I'm going to take a screenshot of this. Control X, and I'm making it as a big picture. So did I need to know. So this is how it works. Now please look at here. Now please look at here. Now I'm using the red color, and now I'm going to design this using, because 81 multiplexer, I'm now using a red color. And what I'm going to do, so when S2 is equal, there are two possibilities. S2 is 0. So what will be my out Y? Help me. So Y will be equal to D0 or D1 or D2 or D3. And if S2 is equal to 1, what is my output? Help me. I need your input.
D4, D4,
D4,
D5, D6, D7.
D5 or D6 or D7. Okay, if you want to do this thingy and you are making only decision based on S2, we are only making a decision based on S2. Okay, so which multiplexer do we need? Only S2. 2 to 1 or 4 to 1?
I think 4 to 1.
No, because there is only one select line. S2. S2 is one select line. You're not getting my point. For the output side, I'm not looking at the output side, because so now what I'm going to do, so I need a 2 to 1 multiplexer, because there is a single select line. So there is a single select line, and now I'm going to do, so basically what I'm going to do, so I'm using some color. My output is Y. So now it depends on S2. S2 has two possible values, 0 or 1. When it's 0, so I'm now this 0, okay, now this 0 is which color? Please look at, I'm using the color. This 0 is which color? 0 is in red color and 1 is in green color. You got it or not got it? Okay. Now if I'm saying for 0, which is the 0 color, so this is, what can I write here? D0 or D1 or D2 or D3, and now I'm using the green color, and then in green color I'm writing D4 or D5 or D6 or D7. Any question? Any question? Is clear or not clear? Clear? I'm not hearing any answer.
Yes, it's clear.
Very good. So I need another multiplexer here. And that multiplexer, now for that I'm now using another color. And now I'm using a blue color. Now it depends on S1 and S0. So I need a 4 to 1 multiplexer or 2 to 1 multiplexer here. Help me.
Four to 1.
Yeah, S1 and S0, there is 0, 0, 0, 1, 1, 0, and 1, 1. It is 0, 0. So D0, then D1, then D2, and then D3. And now what I'm going to do, I'm now using another color. Now I'm using a black color here. So then I need another multiplexer, which is actually S1 and S0, and this is actually 0, 0, 0, 1, 1, 0, and 1, 1. What should I write? Help me here. What should I write here? Please help me. Quick.
D4, D5, D6, D7.
D4, D5, D6, and D7. Any question? Clear? Yes, clear or not clear? If I'm not getting an answer in 6 seconds or 5 seconds, it will not be good for you.
Clear, Professor.
Clear. Okay, so these are possible questions in exam. Design a 16 to 1 multiplexer using 4 to 1 multiplexer. Design an 8 to 1 multiplexer using 2 to 1 multiplexers only. Design an n to 1 multiplexer at gate level. So this is also maybe the question in exam. What will be n? N can be 2, n can be 4, n can be 8, n can be 62, n can be 32, n can be 64, and blah blah blah. So these are all the possible question of exams. Any questions?
Professor, can you go back to the previous page?
Very good. Yes, this I really like it. If you're asking question, I'm very happy. Yes, please go ahead.
In this, can we not use more like 2 to 1 multiplexer?
Yes, you can. Can you see here now? What is this thing? So now we have this. What is this? This is a 4 to 1 multiplexer. So if I'm asking the question, design an 8 to 1 multiplexer using 2 to 1 multiplexer only. Since now this is a 4 to 1 multiplexer. Now this is the blue one. Okay, you can solve it also for the green one. So this is the blue one. So what is this multiplexer here? So if you look at this multiplexer now, the blue one. So okay, now this multiplexer is a 4 to 1 mux. You got it or not got it? And if you go for this the 4 to 1 multiplexer, it can be designed using 2 to 1 multiplexer like this. You got it or not got it?
Got it. Yeah.
So what we do, we copy all of these figures and we paste it here. And we can also copy the same thing and paste it in the green one. But for the green one, the labels will be different. I hope I answered your question.
Yes, Professor. Thank you.
Very good. Any other question? It was a very good question, very thoughtful, very good, very good. Any other question? Should we proceed? Yes or no?
Yes, Professor.
Yes.
Okay, so now we'll proceed. Okay. Now, there is another $1 million question. Okay. What I'm going to do? Oh man, this is. Okay, which gate is this? Okay, it is exclusive OR gate. Okay, this may be the question in exam. So this is a very important question in exam. Maybe very important question in exams up to you. Again. So what is our objective? So please, this is our objective. How can we implement a logic function usage? So this may be the question in exam. Implement an exclusive OR gate using a 2 to 1 multiplexer. Got it or not got it? Okay. Because now what we are going to do, so now this is very important. So please, I need your attention, and I want you to do good in the exam. So please pay attention, and please remember, don't ask ChatGPT. If you ask ChatGPT will become mad for my questions, and you will see it in midterm 1. So please don't. Okay, now we want to design this thing. So we are using a 2 to 1 multiplexer. So what is a 2 to 1 multiplexer? So now it's a red color. What I'm going to do, so now I have a 2 to 1. This is the block diagram of a 2 to 1 multiplexer. It is a select line is S. We have 0 and we have 1. And what is my output? We can assume any output. So we can call this is D0 or D1, and my output is Y. This is the block diagram of a 2 to 1 multiplexer. Clear? This is clear or not clear? Yes or no?
Clear.
Okay. Now we want to implement an exclusive OR gate. So now this is my exclusive OR gate, which is actually the which color? The green color. So now we want to implement an exclusive OR gate. So if I'm saying implement an exclusive OR gate using 2 to 1 multiplexer, what will be the, so can I write an expression for exclusive OR gate? So let's say I'm saying P is equal to M exclusive OR T. Got it or not got it? Can I write something like this? Yes or no? I'm not hearing any answer. I'm sorry.
Yes.
Okay. So can I write something like this? What is the SOP expression for P? Can you tell me what is the SOP expression for P? How can I write it? P is what?
M bar
If I want
T
to
plus
write a SOP
M.
expression, this may be the question in exam. And sometimes, I see some of the answers, they get it from ChatGPT and they answer it very quickly. But I'm asking it during the online lecture, no one is answering me. What will be the SOP expression for P?
M bar T plus MT
Yes,
bar.
very good. M bar T plus what? Plus M T bar. This is clear or not clear? Any question? Okay. Can anyone tell me the expression for Y? Now please remember, I'm now using the red color and the green color. What will be the expression for Y? Anyone may answer. We covered it. What will be the expression for Y?
S bar D0 plus
S
S
bar
D1.
D0 plus S
D1.
Okay. So now there are two equations. Equation number 1 and equation number 2. If you compare equation 1 and equation 2, what is P now? Can you tell me what is now P? So P is the same thing as what? Y. Got it or not got it? And what is the value of S? What is M? Can you tell me what will be M now?
With
S.
the
See,
select
this is
line.
M. M is S, the same thing as S. M is, so it means M is equal to S. So M is equal to the same thing as S. What is now D0 here? What is D0 here? Can you tell me what is D0 here now?
T.
Compare equation 1 and equation 2. D0.
Is it T?
Yes. T. And what about D1? Help me.
T bar.
T bar. So how can we implement it? So my y is equal to now P. So how can we implement it? So I put a P here. And now my D0 is T. D0 is now T. My D1 is now T bar. And my S is equal to M. So this is how we can implement an exclusive OR gate using a 2-to-1 multiplexer. Any question? So in the exam, I may also ask any question. Implement an exclusive NOR gate using 2-to-1 multiplexer. Implement any other gate to the, so you can do some logic and thing like that. Any question? Got it or not got it? This is also how do you derive some expression, and based on that derivation. So what you need to do? So we have a multiplexer. And then you derive the logical expression of that multiplexer. Then you derive the logical implementation of a gate, and then you compare some equations, and based on these equations you draw the final thing. Any question? Clear or not clear?
Clear, Professor.
Clear? Okay, very good. Now you can see here another $1 million question, and this is a $1 million question in exam. So this is example number 1. So basically, can you see here, this is B is equal to K. This is another thing, because this is, okay, please remember, in this example, it's already in the lecture side, and there are some with some animation, and I approve it. So this is actually A exclusive or B. So what I just rename it. I say M exclusive or T. I just change the labels. So in the exam, I will play with a lot of labels. I will play with the labels. I will change a lot of labels, and I will give the labels information. So please be attentive. Don't go for ChatGPT. This is my advice. This is my advice. If you'll go for ChatGPT, you will remorse your decision. Okay. Now, if you look at here, now let's assume if we want to implement this function, and we want to implement this function using an 8-to-1 multiplexer. How can we implement this function using 8-to-1 multiplexer? Can you tell me? Can you tell me? Yes, Thomas. Yes, James. So let's assume if I draw. So let's assume before solving this question, so I want to draw a multiplexer. Okay, so now we want to draw the multiplexer. So we want to design. We want to implement this logic. So what is our objective? So question. So the question is this. So the question is this: implement Y using 8-to-1 mux. If I am solving this question, what should I do? What should be the logical conclusion? What should I do first? Can anyone tell me what should I do first? Anyone may answer. If I want to implement this function using an 8-to-1 multiplexer, what should be the logical conclusion? I'm not drawing the solution, but what should be the first step? Anyone may answer. What should be the first step? Thomas, James, Ghala? How many students are there? There are 22 students. What should be the first step? Abir, Hamad, Zafar, Nuruddin? Yes, what should be the first step? Anyone? If you do not know the answer, say we do not know the answer.
I don't know how you'd usually solve this, but for the expression, I was thinking we could simplify it into like XOR gates and then implement it.
No. Because I want to implement it using a multiplexer. Since I want to, it means that the multiplexer is there. I need to use it. When I need to use it, so what should be the first step to solve this problem? Because the thing in the previous, now if you look at here, whenever I wanted to solve this thing, okay, so when I want to solve any function using a multiplexer, so the first step is to draw the multiplexer. Here, since we are this, we say, okay, now we want to have a 2-to-1 multiplexer. We want to solve this problem using 2-to-1 multiplexer. So first I draw the 2-to-1 multiplexer. So what should I do here in this example? I want to implement this function using a 2-to-1 multiplexer. What should be now the first step? Help me.
Draw the
Now you can answer.
multiplexer.
Draw the multiplex. Simple. We will solve it later on, but at least since we are using it, so we need to draw the multiplexer. So I'm not drawing a 2-to-1 multiplexer. Why? So now it's why it is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And how many select line will be there? Help me.
3.
3. S2, S1, and S0. And what should be this input? D0. What is this thingy? D1, D2, D3, D4, D5, D6, and D7. Any question? It's clear? Okay. Now what is our objective? So our objective is that, okay, now if you now the thing is, so if you want to implement y, so now I'm using different colors. So can I write something? Y is equal to sigma m. Now I'm using different colors. Now the green color, because in the green color I'm now used to, so this is 1. So sigma m of what? This is 0, 0, 1, 2, 3, 4, 5, 6, 7. How can I write in the sigma m form? What should I write here? Help me. Sigma m what?
0, 3, 4, 5.
0. Okay, now I'm going to have a different color. So now I'm using a blue color. So this is actually what? D0, D1, D2, and sorry, basically it is actually what? 0, 3. Clear? 0, 1, 2, 3. What about this color? So let's assume I'm making a black color. What should I write here? Help me. 4. And now I'm using another color. So now let's assume I'm using the orange color. So this is the orange color, which is actually 5. So this is so simple. Now, if you look at here, okay, now then we have 3 inputs, A, B, and C. So this is A, B, and C. So please remember, A is the most significant. So A is the most significant, and C is the least significant. So the most significant should be connected to what? A should be connected here. So we should connect A here, then B here, and then C here. Any question? Okay. Now, what about D0? Where should I connect D0? Can you tell me where should I connect D0? Anyone may answer. D0 should be 1. Then the blue color, D3 should be 1 or VCC, we can call it 1 or VCC. Then it should be 1, and D5, which is actually the orange color, should be 1. What about D1, D2, D6, and D7? Help me.
They should be 0.
Yeah, they should be 0. So we ground them. And we connect all of them. Any question? This is implementing a function using multiplexer is very easy. It's just like a piece of cake. Any question? Now, if you look at here, again we have this thingy. So we want to implement k. K is now given in pi m 157, and the inputs are A, B, C. Let's assume if I'm saying instead of A, B, C, what I'm going to do, let's assume the input are, let's assume we want to solve this function. R is equal to pi m, and R is a function. So let's assume we want to solve this question. R is a function of Q, T, and S. Got it? Okay. And if you want to convert this into sigma function, how can I write here? Sigma m, help me. 0, help me.
2, 3, 4, 6, 8.
2, 3, 4, 6, and 8.
No, 8, my bad.
8 should not be there. Okay. Now we want to have, and we want to design using 8 to 1 multiplexer. So in the first we need to draw the 8 to 1 multiplexer. So I can use the black color for it. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. What should I connect? Q, T, and S. So Q should be here because this is Q, T, and S should be there. My output is, what should be my output? Help me. Label it. Anyone may answer.
R.
R. Okay. So now for the blue color, 157. So 157. So can you see this is 1, this is 5, and this is 7. So this, all of them should be connected to VCC, which is actually 1. And the red one, this, 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 this. So this is 0, 3, sorry, 0, 2, 3, 0, 2, 3, 4, 6. 4 and then 6. All of them should be connected to what? Any question? Clear or
So
not
why
clear?
is it the opposite?
Why?
Because pi m we are
Oh,
counting zeros.
no, there's a thing. There's a thing. Very good. Very good. You nailed it. It means you are the only one who is what? Yes. You're the only one. How can I use the rubber? Where is it? Any rubber here?
Yeah,
So
this
maybe I will use. So basically what I can do, so I can increase its size and I can make it more color, make it like this. You're totally right. You're totally right. All of the students are sleeping except you. Okay, so now what I'm going to do, very good observation. So I can make it the color, so I can make it this color. So since it is 0, so what for the blue one, I can ground it. And for the red one, tell me. This is thank you, and I think thank you for your attention. I really like it. Thank you. Any question? Is it clear now? Is it clear now?
Yes, it's clear.
yes.
Okay. I can just I can just make it, because I just want to remove the ground here. Okay, so this is how it works. Okay, this is how it works. Oh, now this is a priority encoder. Okay, now we have very less time, so I'm now going to make it more fast. So now let's assume there are different students. Okay, so now there are different students. So let's assume we have different students, which is A3. So I will, let's assume we have different students. We have A3, which is actually, let's assume Thomas, T stand for Thomas, and let's assume this is Ghala, and let's assume this is Abir, and let's assume this is James. Okay, so now let's assume we have a priority encoder and we want to design a priority encoder using multiplexer, and let's assume we say that Thomas has got the highest priority, okay, and James has got the lowest priority. Got it or not got it? So let's assume, and now can you see here this E3, this is actually A3, this is E3, so this is actually the priority for Thomas, this E2 is the priority for Ghala, and this E1 is the priority for Abir, okay, and the lowest priority, the poor guy, the James guy. Okay, so now let's assume if we say, so E3, then we have E2, then we have E1, okay, and let's assume, so let's assume if this is Z1, E3 is 1 and 0 and 1, So who are making request? Who is making request? Who is making request? It means that E3 is 1. So Thomas is making request E3, and who is making request E1? E1, who is E1? So it means that Abir is making request, or Abir. Whom I will serve? Thomas or Abir? Anyone may answer.
Thomas.
Thomas. Why? Because Thomas has got the highest priority. Got it or not got it? Okay. Now assume another scenario. Let's assume Thomas' hand is down. Okay. So let's assume this is actually E2 and E1. So it means who is requesting? E2 is requesting, and E2 is actually whom? Whom is Ghala or Abir is requesting, but Ghala has got the highest priority, so E2 has got the highest priority. So now in this case, who will be serviced? Ghala will be served. And if both of them are 1 and E1 is 1, so E1 is 1, so A1 will be serviced because there is a single request, so it means that Abir will be serviced. Got it? And all of them are 0. If all of them are 0, so the lowest priority is for James. Any question? So this is how we need to design it. So how can we design this encoder using multiplexers? I will explain this one in an example. Okay, so now we want to have the priority encoder. Okay, now, so it means that E3 is 1. If E3 is 1, so now I'm using this color. So if E3 is 1, we ignore E2 and E1. And what is my output? My output is now S. My output is S. So can you see here? So now we need a 2-to-1 multiplexer. Now it depends on E3. There are two possible values of E3. E3 will be either 1, 0, or E3 will be 1. If E3 is 1, what will be my S here? Help me. My S will be A3. But if E3 is 0, what should be the value of S? Because this E3 is 0 now. So if E3 is 0, so now we are saying E3 is 0. When E3 is 0, what will be my output? My output will be what?
A2, A1, or A0.
Or A2 or A1 or A0. Now we need to check for E2. So we need another. So we need to check for E2. This is my E2. So when we have E2, so now we have E2 here. There are two possible values of E2. It is 0 or 1. If it is 1, who will pass? A2. A2 will pass there. And then if it is 0, what will be my output? Help me. If it is 0.
A1 or A0.
A1 or A0. And then we need another multiplexer. So now I'm using a black color. We have then, can you see here? We have now E1. There are two possible values. It is actually 0 or 1. It is 0. Help me. Will pass. Yes?
A0.
A0 and 1. A1. Clear? So this is how we can design a priority encoder using multiplexer. Okay, now take another example. So let's assume we have, okay, now take this example. So let's assume E3 is equal to 0, E2 is equal to 1, and E1 is also 1. So assume this example. So E3 is equal to 0. So basically this will not pass, so this value will pass. So can you see here? Who will pass here? This will pass here. But it now depends on E2. So E2 is 1, so A2 is 1, so A2 will be 1. And E1 is ignored. Any question? Clear or not clear?
Clear.
Clear? Any question? So now what I'm going to do, so I'm going to explain this with another thing. So basically what I'm going to do, so now the screen will be hidden now. So now what I'm going to do now, I can now share the application screen. Is the screen visible now? Help me.
It's not visible.
No, it's visible now. Visible?
Yeah, now it's visible.
Okay, so now this is the diagram of this. So can you see here? Now it depends on, can you see now with the red color? If you look at the red color, if E3 is 1, who will pass? A3 will pass. And we ignored all of these values. Now we need to check for, and A3 will pass. Because you know, E3 will be 1. See, E3 will be 1. So this is another signal. Maybe this is D0. So we will ignore D0. Doesn't matter. Okay. Now the second condition. With E3 is equal to 0. E3 is 0, 0. Who will pass? A2 will pass. Why A2 will pass? Now E2 is 1. Since E2 is 1, so here A2 will come from here and got it or not got it? And now if both of the E3 are E3 is 0 and E2 is 0. E3 is 0 and E2 is 0. Both of them are 0, 0. Now it depends on E1. If E1 is 1, so A1 will pass. Got it or not got it? And if all of them are 0, the poor gems 0, 0, 0. So the poor gems pass here and then it will be here. Any question? Clear or not clear?
Clear, Professor.
Very good. So who has got the highest priority? Highest priority is A3, which was Thomas, and the lowest priority is A0, which is the poor James. So now it is a multiplexer, and remember there are some things. So now this is now we in the previous step, so we have encoder. So the opposite of encoder is decoder, and the opposite of decoder is encoder. So they are like just like the opposite of each other. So now what we will study is now we will study a demultiplexer. So this is now we will study a demultiplexer. It has one input and it some select lines, and there are some outputs. So can you see here? This is a 2 to it is 1 to. Okay, please remember, if we have a 2 to 1 multiplexer, so we have 1 to 2 demultiplexer. So there are two possible values. When s is equal to 0, what will be the value of d0? 0. When s is equal to 1, what will be the value of d1? D1 will be a. Clear? So a will pass to d0 and will pass to d1. So this is a 4 to 1 multiplexer. If s1 and s0 0, 0. Where B will pass? B will go where? Anyone may answer. Where B will go?
D0.
D0. We will go to D0. If it is 0, 1, B will go to D1. If it is 1, 0, B will go to D2. And if it is 1, 1, B will go to D3. Got it? So this is how it works. And now I will explain this in an example. Okay, so what I'm going to do, so I'm going to, and maybe the screen will also not be available. I'll explain it. No problem. I'll explain it. Is the screen visible to you now? Got it or not got it?
It's not visible.
Okay, now instead of doing this, what I'm going to do, so I want to design, so we want to design 8 to 1 demultiplexer. Okay, 4 to 1 is there, but I want to design it. Now it's visible, screen is visible now? Yes or no?
Yes.
Yes.
Okay, so now we want to design one to 8 demultiplexer, and now this 1 to 8 demultiplexer. So if we have 1 to 8 demultiplexer, so let's assume, please remember, this is very important. So if you want to design 1 to 8 demultiplexer, so let's assume that S1, S2, S1 and S0 is actually 100. So this is 100. So this is actually the index for 4. What will be my K? K in this example will be what? K will be equal to D4. And what will be, I'm sorry. So what will be D4? D4 will be equal to what? D4 will be equal to K. What about D0? What about D1? What about D2? What about D3? What about D5? What about D6? What about D7? All of them will be 0. Clear or not clear? So now we take another example. So let's assume we have this DMux. Okay, this DMux. So this is D0, then D1, D2, D3, D4, D5, D6, and D7, and this is J. I'm now changing the thing. And now we have S2, S1, and S0. Clear? So let's assume S2, S1, and S0 is 110. What will be the value of, what will be the output? Can anyone tell me? Anyone may answer.
D6 is equal to G.
Yes. So in this case, 110 is the index of 6. So it means that D6 will be equal to J. What about D0, D1, D2, D3, D4, D5 and D7? All of them will be what? 0. So in this case, D6 will be equal to J, and all of the remaining, and I'm using the blue color for it, so all of them will be 0. So there will be 0, 0, 0, 0, 0, 0 and 0. Any question? Okay, now how can we design this multiplexer? So let's assume we have another this multiplexer. So now this is a multiplexer, and now this is very simple. So let's assume this input is R, and now we have S1 and S0. So S1 and S0, we have 0, 0, we have 0, 1, this we have 1, 0, we have 1, 1. Got it or not got it? So now we have D0, then we have D1, then we have D2, and then we have D3. Clear? Okay, now what will be the expression for D0? Can anyone tell me? So now I'm using the red color for D0. So D0 is the red color. What is the expression for D0? So this is actually S1 and S0. Got it? So D0 is S1 and S0 and then R. So this is 0, 0. So it's 0, 0. It means 0, 0. What will be the expression for D1? Can anyone tell me? The green color. It's 0, 1, S1 and S0. And then we can say R. Yes, can you tell me? What will the expression? Anyone may answer?
Bar
No
on
answer means
S1.
got it. What will be the expression for D2? Anyone may answer. What will be the expression for D2?
S1 S0 bar R.
Yeah. And what will be the value for D3?
S1 S0 R.
Okay, now take some value. Assume that S1 is 1 and S0 is 0. So if it's 1, so it means that, okay, now can you see here? So what will be D0? So please, D0 is actually what? D0 is actually S1 bar S0 bar R. D1 is S1 bar S0 R. And D2 is what? S1 S0 bar and R. And D3 is what? S3 is S1 S0 R. Since S0 is 0, S0 is 0. So S0 is 0, so this will be equal to 0. And this will also be equal to 0. And S1 is 1. So when S1 is 1, so it will be equal to 1 bar dot 0 bar. Got it? And 1 bar, S1 is 1. 1 bar, it will be equal to 0.1, it will be 0. So it will also be 0. And in this case, it will be R. Any question? Is clear or not clear?
Professor, in the last D3, how will it be 0?
Because S0 is 0.
But isn't it 1, 1?
No, it's I'm assuming that S1 is 1 and S0 is 0. For the input, input can be anything. This is the expression. S1 is 0 R. This is the expression. This is the expression. And this is the expression, and this is the input combination. You are not getting my point now.
No, Professor, I got it. Thank you.
Not? You got it?
Yeah.
If I change the combination, if S1 is 1 and S0 is 1, so D3 will be equal to R and all of the other will be 0. I hope I answered your question.
Yes, Professor. Thank you.